It's my privilege to introduce, first of all, this evening, my colleague Matt Lunsford. Matt is professor of mathematics here at Union University, where he's been a faculty member since 1993. Over the past 20 years, he's served the university in various capacities, including mathematics discipline coordinator, associate dean of the College of Arts and Sciences, chair of the Faculty Development Committee, and chair of the Pew Research Selection Committee. His research interests include classical Galois theory, I should have read this before, mathematics, pedagogy, and the history of mathematics. When he's not reading C.S. Lewis, he enjoys the works of Tolkien, Dostoevsky, and Tolstoy. He and his wife, Deanna, have 3 children, Cara, Thomas, and Emma. Join me in welcoming my colleague, Matt Lunsford.
Good evening. Thank you, Dr. Mitchell, for that very, very kind introduction. And I want to express my thanks to Dr. Barnard for inviting me to give this lecture this evening. I know that he cannot be here with us. But I also want to thank each of you, members of the audience here in Jackson and also in Germantown and Hendersonville, for your attention this evening. The title of my talk is The Mathematical Mind of C.S. Lewis. And you might be asking, what is a mathematician doing giving a talk on Lewis? And you might even be hoping that there's not very much to say. We'll see about that. I first read Lewis as an adult, not as a child, and I began with his apologetic works, Mere Christianity, Miracles, Abolition of Man, Problem of Pain, and then I continued reading. Later, I read the science fiction trilogy and finally the Narnia series. So reading Lewis became addictive because each book or essay or story had the power to expand my way of thinking about something very important to me, my Christian faith. Hence, Lewis became one of my favorite authors to read, to enjoy, and even more so, a mentor to me as a model of what a Christian scholar should be in the academic world. Let's begin this journey together with a quote from Lewis. I could never have gone very far in any science because on the path of every science, the lion, mathematics, lies in wait for you. Even in mathematics, what could be done by mere reasoning, as in simple geometry, I did with delight. But the moment calculation came in, I was helpless. I grasped the principles, but my answers were always wrong. Yet, though I could never have been a scientist, I had scientific as well as imaginative impulses, and I loved ratiocination. It's going to be one of the 2 big words tonight, ratiocination. Lewis's education was classical, and therefore he did learn some elementary geometry from Oldie, his first tutor. You should read about Oldie in Surprised by Joy. But he was not, that is Lewis, was not very good at algebra. In fact, Lewis failed the math portion of Responsions, the entrance examination to Oxford, at least twice, he admits, maybe more. I think he wanted to forget about it. He was finally admitted to Oxford on a waiver due to his service in the First World War. In the quote, Lewis admits that he could never have been a scientist because of the necessity of mathematics, yet he possessed 2 key aspects of a mathematical mind, ratiocination and imagination. And so it's these 2 ideas that I want us to consider more thoroughly this evening. So what do I mean by ratiocination? It's the process of logical reasoning. Listen to Lewis in this quote, and this will be the first of many Lewis quotes that you will hear over the next hour. Lewis says the answer is that at least one kind of thought, logical thought, cannot be subjective and irrelevant to the real universe. For unless thought is valid, we have no reason to believe in the real universe. I conclude then that logic is a real insight into the way to the way in which real things exist. In other words, the laws of thought are also the laws of things in the remotest space and the remotest time. So many readers, including myself, are drawn to the works of Lewis because of his logical reasoning and his ability to articulate his thoughts with great clarity. One contemporary author puts it this way: where would the Christian thinker be without Lewis? He is pivotal. But the other side of the coin I want to consider is imagination, the ability of the mind to be creative or resourceful. When asked about writing The Lion, the Witch, and the Wardrobe, Lewis remarked, and beginning the quote, "One thing I am sure of. All 7 Narnian books and my 3 science fiction books began with seeing pictures in my head. At first, they were not a story, just pictures. The Lion, the Witch, and the Wardrobe all began with the picture of a fawn carrying an umbrella and parcels in a snowy wood. This picture had been in my mind since I was about 16. Then one day, when I was about 40, I said to myself, let's try to make a story about it. So you see that, in a sense, I know very little about how this story was born. That is, I don't know where the pictures came from, and I don't believe anyone knows exactly how he makes things up. Making up is a very mysterious thing. When you have an idea, could you tell anyone exactly how you thought of it? In this clip taken from the Chronicles of Narnia movie based upon The Lion, the Witch, and the Wardrobe, we're going to see both of these 2 ideas, these aspects, ratiocination and imagination, on display. In this clip, there will be 4 children. Lucy and Edmund have just returned from Narnia, but the older siblings, Peter and Susan, are skeptical. The Pevensey children encounter Professor Kirk, the man in whose home they are staying during the bombing of London in World War II. And the character Kirk is important because he's obviously a tribute by Lewis to his secondary tutor following Oldie, Mr. Kirkpatrick, who the family referred to as Kirk. It seems that Lewis owes much of his power of ratiocination to his days of tutelage under Kirk. So I want you to attend to the logic of the professor as he helps the older siblings decide who is telling the truth about Narnia, Lucy or Edmund.
What are you talking about?
Narnia, it's all in the wardrobe like I told you.
Oh, you've just been dreaming, Lucy.
But I haven't. I saw Mr. Thomas again, and this time Edmund went too.
You saw the fawn?
Well, he didn't actually go there with me. What were you doing, Edmund?
I was just playing along. I'm sorry, Peter. I shouldn't have encouraged her, but you know what little children are like these days? They just don't know when to stop pretending.
Ow! Oh! You children are one shenanigan shy of sleeping in the stable. Professor, I'm sorry. I told them you were not to be disturbed.
It's all right, Mrs. McCready. I'm sure there's an explanation. But first of all, I think this one is in need of a little hot chocolate.
Come along, dear.
You seem to have upset the delicate internal balance of my housekeeper.
We're very sorry, sir. It won't happen again.
It's our sister, sir. Lucy.
The weeping girl.
Yes, sir. She's upset.
Hence the weeping.
It's nothing. We can handle it.
Oh, I can see that.
She thinks she's found a magical land in the upstairs wardrobe.
What did you say?
The wardrobe upstairs. Lucy thinks she's found a forest inside.
She won't stop going on about it.
What was it like?
Like talking to a lunatic.
No, not her, the forest.
You're not saying you believe her?
You don't?
Well, of course not. I mean, logically, it's impossible.
What do they teach in schools these days?
Edmund said they were only pretending.
And he's usually the more truthful one, is he?
No. This would be the first time.
Well, if she's not mad and she's not lying, then logically, we must assume she's telling the truth.
You're saying that we should just believe her?
She's your sister, isn't she? You're a family. You might just try acting like one.
So it's a great clip, and if she's not lying and she's not mad, then logically she must be telling the truth. That echoes a quote that you'll also find in Mere Christianity about Jesus the Christ. And so I invite you to find that in Mere Christianity, very similar to what you hear in this clip here. But what does all of this have to do with math? So that's the next question that I want to address. Maybe the hardest part of my talk this evening is to change your perception of the true nature of mathematics. See, many people think that math is nothing more than a bitter pill. So follow along in this quote. But what if math isn't a bitter pill? The radical proposal is that mathematics isn't a set of rote practices for solving problems. Those are merely what remain when discoveries harden into techniques. Let me say that again. Those are merely what remain when discoveries harden into techniques. To the contrary, the essence of math is play, a form of reasoned discovery motivated by curiosity and insight. If Hennebree is correct, he's at Boston University and not a mathematician, by the way. If he is correct, and I certainly agree with him, then mathematics is a form of reasoned discovery motivated by curiosity and insight. That means that mathematics is a combination of ratiocination and imagination. Consider this model with me of the mathematical method. This model was formulated by Professor Keith Devlin of Stanford University. And the model goes something like this. We have the real world. We try to capture things in the real world with a mathematical description. We study that mathematical description. We see its properties, things that we can do, and we create what are called mathematical processes. Those mathematical processes are then used to feed back information into the real world. Now, many people confuse the essence of mathematics with the mathematical processes that are taught and memorized. Of course, the mathematical processes are an important part of the discipline and are very valuable to many other areas of human knowledge. For instance, physics, I see a physicist in the back, chemistry, engineering, computer science, economics, just to name a few. But these processes do not constitute the whole of the discipline. What is missing here is the ingenuity needed to create a mathematical model and the deductive reasoning necessary to produce the rigorous set of mathematical processes. In other words, if we learn only the mathematical processes, then to a large degree we have omitted the aspects of ratiocination and imagination from the discipline. So here's an example of the method that most of us in the room will already be somewhat familiar with. You see, mathematics is very, very good at modeling many features of the real world. And one such feature, which calculus does, is modeling the motion of an object. So if the object, for example, is a free-falling object, then its position is given by a quadratic relationship between distance and time. So to study this motion, one must become familiar with quadratic equations. In studying these equations, one is usually introduced to the infamous quadratic formula. Some of you can still quote it. Unfortunately, this part of the model, the mathematical processes of applying the quadratic formula to quadratic equations, is often all that is remembered of the entire model. Just the infamous quadratic formula, nothing else. So what I would like to do is ask that you would indulge me for a few minutes as I try to present to you an alternative view of mathematics. That is, I want to convince you that math is not a bitter pill. So let me begin with a famous problem from the history of the discipline. This problem was solved by the mathematician Leonhard Euler in the first half of the 18th century. And what you see here is a picture of a city, Konigsberg, which is now Kaliningrad in modern-day Russia. Next to the picture is a letter that Euler is writing to one of his colleagues. And let me read that letter to you, or this part of the letter. He says, "A problem was posed to me about an island in the city of Konigsberg, surrounded by a river spanned by 7 bridges, and I was asked whether someone could traverse the separate bridges in a connected walk in such a way that each bridge is crossed only once. I was informed that hitherto no one had demonstrated the possibility of doing this or shown that it was impossible." What a great unsolved problem. Right? This is a problem sitting right there in a real city in the 18th century. But how should one go about searching for a solution? Well, the solution begins, going back to our model, with a mathematical description of the problem. In this case, we need imagination. So Euler transferred the relevant information from the map to the model. In this case, he was left with each landmass being represented by a point, which we call a vertex, and each bridge was replaced by a curved line segment called an edge. And the resulting model is what we call a graph. That's what you see on the right. By analyzing this graph, Euler demonstrated, ratiocination, that the desired connected walk that the people of the city were looking for was in fact impossible. Moreover, one would need an even number of bridges emanating from each landmass for a connected walk to be possible. This gives a complete solution to the problem. As it is, it's impossible. If you want to fix it, make sure that you have an even number of bridges coming out of each landmass. But this is not the end of the story. If this were the only thing that came from Euler's solution, well, that would be a nice problem that was solved. But the insight gained here by Euler has helped solve numerous other problems and actually initiated a new field of study in mathematics, which is known as topology. So where else can we use the ideas of Euler? Well, how about the map coloring problem? Here's something cartographers have been studying for years and years. How many colors does it take to color a map? So the question, if we want to state it very clearly, is what is the minimum number of colors that always suffice to color any potential world map? So here's a different problem, but it can be tackled with very similar ideas. So what is the minimum number of colors that always will suffice to color any potential world map? Note here in the map of the United States that 4 colors will suffice. It is also clear that 4 colors are necessary. Let me show you that. You might think that we would need to look at the 4 corner states, but actually the way that this works, 2 states have to be colored a different color if their boundary is more than a point. So the 4 corner states actually only need 2 colors, even though in this map I think they're colored in more than 2. But the problem is not the 4 corner states. It's actually Nevada. Anybody from Nevada? Are you really? So you're the problem. Let me explain. Nevada is surrounded by 5 states. And so Nevada gets a color. And then we'll start at the top with Oregon. Oregon can't share the same color with Nevada. We get to California. Now we need 3 colors. Okay. Let's move over to Idaho. That can have the same color as California. And Utah will color the same as Oregon. But what about Arizona? Well, Arizona touches Utah, California, Nevada, and we are forced into a 4th color. Okay. So not only will 4 suffice, but 4 are necessary for this particular coloring of the United States. What about other maps? Well, would you believe Euler's insight will help us here? Actually, a proof that 6 colors will suffice for any map follows fairly easily from Euler's ideas. That is, we make a graph in which the states are vertices and the edges are drawn between vertices that share a boundary of more than a single point. So you can see the graph here connecting the states. However, map makers noticed that I could seem to get by with less than 6. And it takes a considerable more effort in order to reduce that number below 6. But Euler's ideas get us to 6 pretty quickly. So more effort was required to show that 4 colors will actually suffice for any map drawn on a flat sheet of paper or on a globe or sphere. This result, known as the 4-color theorem, was finally proved in 1976 by 2 mathematicians at the University of Illinois. And here's an interesting fact about that theorem. It's the first fully accepted mathematical theorem that used computer programming to aid in the details of the proof. Pretty important result. So Euler's idea of solving the bridge problem in Konigsberg led to a solution of the map coloring problem, but it leads mathematicians with their imagination to think of other things. So I said that 4 colors would suffice for any map drawn on a flat sheet of paper or on a globe or sphere. But what if we let our imagination run away with us? Suppose out there's a solar system. And in that solar system, there's a planet, and it's in the shape of a donut. We call that a torus. Not Taurus, but torus. If such a world would exist, it might take as many as 7 colors to color the map of this world. Notice the image on the right. The country that's colored white touches 6 other countries. It touches the red and the purple, the yellow and the orange, the blue and the green. Okay. So on this strange planet, we would have a 7-color theorem. Now, what does that mean? Well, in terms of topology, this new area of mathematics that Euler began, the flat surface, the sphere, and the torus, they have to be different because they have different map coloring properties. So thank you for indulging me here for a minute in mathematics, and I hope that these examples in topology, the Konigsberg bridge problem, and this 4-color theorem have helped to reorient your view of mathematics. But this is a talk about Lewis, so let's return to Lewis and his mathematical mind. First of all, I want to talk about ratiocination, his logical reasoning. You see, Lewis believed that natural law, or the moral law, was akin to the rules of mathematics, in that both are not mere conventions, but in fact are real things. Hence, it's no surprise that Lewis would use his ratiocination skills in moral decision-making. And he does that in this essay, Why I'm Not a Pacifist. Before we get to the essay, let's listen to Lewis talk about the moral law. I believe that the primary moral principles on which all others depend are rationally perceived. We just see that there is no reason why my neighbor's happiness should be sacrificed to my own. We just see that things which are equal to the same thing are equal to one another. It is because all morality is based on such self-evident principles that we say to a man, when we would recall him to right conduct, be reasonable. In the essay, Why I'm Not a Pacifist, Lewis addresses this issue of pacifism, and he models his argument against total pacifism on a geometric proof, complete with axioms, definitions, theorems, and the argument. But Lewis uses different terminology than the mathematician. He says reception of facts. The mathematicians in the room, we would call this definitions and theorems. Self-evident truths, we would say axioms or postulates. And logical arrangement of facts and truths to produce, well, we would say a proof, right? And Lewis says this is a proof as well. Lewis says the disagreement often arises when the two categories of facts and self-evident truths are confused. So for Lewis, on the topic of pacifism, the self-evident truth about war is that it is better to help than to harm. But he does make this comment that sometimes helping one might mean harming someone else. And the facts about war are this for Lewis. Not that it is necessarily always wrong, but that it is very, very disagreeable. And you have to remember, Lewis was in the First World War in the trenches. He also says that neither human nor divine authority can be used to support total pacifism. That's his view. Therefore, he concludes that it's very likely that total pacifism is not morally correct. So let me read to you from the essay. This, then, is why I'm not a pacifist. If I tried to become one, I should find a very doubtful factual basis, an obscure train of reasoning, a weight of authority, both human and divine, against me, and strong reasons for suspecting that my wishes had directed my decision. As I have said, moral decisions do not admit mathematical certainty. It may be, after all, that pacifism is right, but it seems to me very, very long odds, longer odds than I would care to take with the voice of almost all of humanity against me. Now, other arguments of Lewis using this deductive reasoning appear in other places. For example, in Mere Christianity, Lewis argues that the moral conscience given to humans, which in the Abolition of Man he calls the Tao, is evidence of a divine moral being. Hence, becomes an argument against atheism. Listen to Lewis. The moment you say that one set of moral ideas can be better than another, you are in fact measuring them both by a standard, saying that one of them conforms to that standard more nearly than the other. But the standard that measures two things is something different from either. You are in fact comparing them both with some real morality, admitting that there is such a thing as a real right, capital R, independent of what people think, and that some people's ideas get nearer to that real right than others. And then in another apologetic work, Miracles, Lewis argues that rational thought given to humans is evidence of a divine rational being. I have a thought that we probably will hear a little bit more about miracles in the second talk. Lewis claims that no thought is valid if it can be fully explained as the result of non-rational causes. Let me say that again. Lewis claims that no thought is valid if it can be explained as the result of non-rational causes. Hence, he gives an argument against naturalism. So let me read this quote. The whole picture professes to depend upon inferences from observed facts. Unless inference is valid, the whole picture disappears. Unless we can be sure that reality in the remotest nebula or the remotest part obeys the thought laws of the human scientist here and now in his laboratory. In other words, unless reason is an absolute, all is in ruins. Yet those who ask me to believe this world picture also ask me to believe that reason is simply the unforeseen, unintended byproduct of mindless matter at one stage of its endless and aimless becoming. Here is flat contradiction. Let's move to Lewis's imagination. So I want to begin with the essay Transposition, which appears in the work Weight of Glory. In this essay, Lewis discusses the barrier that exists between the spiritual man and the natural man. He begins with the claim that not all things can be put into one-to-one correspondence. Some things are richer and some things are poorer, says Lewis. For example, emotions and sensations. Multiple emotions can produce the same sensation. For example, joy and sadness might result in tears. In a similar way, the spiritual cannot be explained completely in natural terms. Often it is virtually impossible to communicate spiritual ideas using only the language of natural things. So in order to elucidate these thoughts, Lewis opts for several analogies. So listen to Lewis from this essay. And the skeptic's conclusion that the so-called spiritual is really derived from the natural, that it is a mirage or projection or imaginary extension of the natural, is also exactly what we should expect. For as we have seen, this is the mistake that an observer who knew only the lower medium would be bound to make in every case of transposition. The brutal man can never, by analysis, find anything but lust in love. The Flatlander never can find anything but flat shapes in a picture. Physiology never can find anything in thought except twitching of the gray matter. It is no good browbeating the critic who approaches transposition from below. On the evidence available to him, his conclusion is the only one possible. So one analogy that Lewis uses over and over, and it's here in this passage, is that of dimensionality. For example, he says the Flatlander never can find anything but flat shapes in a picture. So what does Lewis mean when he says Flatlander? I say clearly Lewis was heavily influenced by a novella by the name of Flatland, a romance of many dimensions. If you haven't read Lewis, read Lewis. If you haven't read Flatland, read Flatland. It's a great book. Flatland is a work of mathematical fiction, not science fiction, it's mathematical fiction, written by an educator and clergyman, Edwin A. Abbott. So the work was first published in 1884. It's a very cleverly written satire of British life in the second half of the 19th century. The satire targets the Victorian class structure, and we see this in the way that men and women are portrayed by geometric shapes. Women are one-dimensional shapes. Men are two-dimensional shapes. And the more sides that a man has, the higher he is in society. It also targets the prevailing worldview of rationalism. So the book talks about this idea of you have to see it to believe it. And the men are that way. They're very rational in the book. The women are not. They're much more emotional with feelings. And finally, the satire targets the emerging theory of Darwinism. So in Flatland, everyone gets better with the next generation. And in fact, the parents pay homage to their children because they have gained more sides. Therefore, they are more advanced. Even with all of this satire, though, Abbott says that one of the major goals of the book is the enlargement of the imagination. And Abbott uses travel through different dimensional worlds as a means to enlarge the reader's imagination. Furthermore, he utilizes the dilemma of communication between inhabitants of different dimensional worlds to foster humility. And so what is this dilemma? Because this is really key. What's the dilemma that comes about in Flatland as inhabitants of different worlds try to communicate? So I would say it this way. How does an inhabitant of a higher dimensional world translate the reality of his world into the vocabulary of a resident of a lower dimensional world? This is the richer to the poorer. How does the richer communicate to the poor? The net effect of this communication gap is a dichotomy that forces the residents in the lower dimensional worlds into one of two collections. Either using imagination and reasoning, they are led to accept by faith the existence of the higher dimensional worlds, or by lack of aspiration and stubborn ignorance, they reject the truth of these new worlds. So a little bit more about Flatland. It is the story of A Square. A Square. He's a regular inhabitant of a two-dimensional world called Flatland. Through dreams and revelations, A Square is transported to worlds of other dimensions. First to a one-dimensional world called Lineland, and later to a three-dimensional world, Spaceland, akin to where we live. Each experience prepares A Square for his ultimate destiny to be an apostle of the gospel of three dimensions to his fellow Flatlanders. In the 21st century, this classic work was made into a computer-animated film, about 30 minutes long. I'm going to show you a short clip from the film. And in this clip, A Square and his daughter Hex, short for hexagon, discuss the fundamental concepts of dimensionality. Let's see if I can get this right. No.
Arthur!
Oh, sorry. What is it?
Arthur, dear, have you been listening? Hex asked you a question.
Grandpa, today the schoolmaster told us about the Circle's new proclamation, and I have a question.
Go ahead, Hex.
What exactly is a dimension?
Well, it might be hard to explain.
Everything is so hard to explain.
But you know what? I used to do quite a bit of geometry in my day. Okay, let's pretend this is a point in space, and we extend it 3 units. We have what? We have 3 to the first power, right?
Mm-hmm.
All right. We also have a one-dimensional line segment that is 3 units long. So if we take this line segment of 3 units and move it 3 units parallel to itself, we make a square of 3 units on each side, or 3 times 3, 3 to the second power.
9 units in the square.
Smart girl.
I've seen this before.
Hmm? Where?
It looks so familiar. I remember now. I once saw a picture of Area 33H.
Area 33H?
Yeah, you know, the old ruins.
Please, Hex, you're too smart to listen to those conspiracy theories.
Some people say they're a sign.
Those people should watch what they say.
Grandpa, if a point moves 3 units, that's 3 in the first power, then that line segment moves parallel to itself, making a square of 9 units, 3 to the second power. So it must be that a square moving, somehow parallel to itself, can make something else, like a super square that represents 3 to the third power, or 27 units. That's so hard to imagine, but wouldn't that be amazing? A super square? In the third dimension?
Please,
Maybe
Hex.
a super hexagon?
Hex.
It would be...
You know the Circle's proclamation. It's too dangerous to believe in such foolishness.
Why?
Why? Because the Circles are wise. That's why.
What makes them so wise?
Their configuration, of course. Their infinite size.
I
Hex.
wonder what's so special about Area 33H.
Hex!
I bet it has a clue to explain all this. I bet if we could get there, we'd see a super square. Or maybe even a super hexagon.
Hex, enough! No grandchild of mine will meddle with such heresy. Go to your room, now.
In this diagram, we can see what the granddaughter, Hex, was discussing with her dad in the clip. She was using her imagination to visualize the cube, which we see there in the middle. Now, that's no problem for us Spacelanders. However, we have an analogous problem attempting to visualize a tesseract, which is a four-dimensional cube. So consider, looking at the last picture there in the diagram, consider moving a cube parallel to itself in some direction that we don't perceive. We don't know how to do that. But if we could do that, then we would have the four-dimensional cube, the tesseract. Now, the tesseract has become a popular object in literature and film of late. It appeared first, to my knowledge, in Madeleine L'Engle's children's novel, A Wrinkle in Time. And for those of you that are fans of the Avengers movies, of course, the tesseract is there. And so now you know what it is. It's a four-dimensional cube. This next diagram is also taken from Flatland, and this diagram depicts the main character, A Square, and he is labeled myself as the square. His visit to the one-dimensional world of Lineland, and you'll notice directly beneath myself, A Square, is someone labeled the king. He's a small line segment in Lineland. The king of Lineland was not convinced of a second dimension by the visit of A Square, and he thought that A Square was some charlatan or conjurer. Now later in Flatland, Square is visited by a being from the third dimension, a sphere, a globe. And Square draws exactly the same conclusions as the king. He doesn't believe it. Sometimes we never learn from our own mistakes or even from the mistakes of others. But you know, Lewis and Abbott discovered something significant here, something significantly true about the Christian life. And that is, it is difficult to communicate the existence of the spiritual realm, which is the higher dimensional world, to those who believe only in the natural world, which is the lower dimensional world. Even in the novella, Sphere convinces A Square of the existence of the third dimension only after a radical experience of removing him altogether from Flatland so that he could see it from Spaceland. You might say Square had a conversion experience. Now, transposition is not the only work of Lewis that uses this idea of analogy of dimensions. In The Silver Chair, the next to last book in the Narnia series, this notion appears in a dialogue between the Queen of the Underland and Prince Rilian of Narnia as they discuss whether or not the overworld, Narnia, really exists. The Queen says, "You have seen lamps, so you imagined a bigger and better lamp, and you called it a sun. You've seen cats, and now you want a bigger and better cat, and so you called it a lion. And look how you can put nothing into your make-believe world without copying it from the real world, this world of mine, which is the only world. There is no Narnia, no overworld, no sky, no sun, no Aslan." And the quote rings home the difficulty of using the vocabulary. Those who knew of Narnia could only express it in terms of the vocabulary in the lower world, and that caused a dilemma, a communication dilemma. In other writings, Lewis uses the analogy of dimensions to discuss the mystery of the Trinity, the incarnation, the resurrection of the body, God's relationship to time, and even to eternal life. For instance, in the essay, The Poison of Subjectivism, he writes, Flatlanders attempting to imagine a cube would either imagine the 6 squares, the sides and top and bottom, coinciding, and thus destroy their distinctiveness, or else imagine them set out side by side and thus destroy the unity. Our difficulties about the Trinity are of much the same kind, says Lewis. In A Grief Observed, the analogy is applied to temporal and eternal life. Following the death of his wife, Joy Davidman, Lewis writes, "Suppose that the earthly lives she and I shared for a few years are in reality only the basis for, or prelude to, or earthly appearance of 2 unimaginable, supercosmic, eternal somethings. Those somethings could be pictured as spheres or globes, where the plane of nature cut through them, that is, in earthly life, they appear as 2 circles that touched. But those 2 circles, above all the point at which they touched, are the very thing I am mourning for, famished for, homesick for. You tell me," she goes on, "but my heart and body are crying out, come back, come back. Be a circle touching my circle on the plane of nature." Can we, on this side of eternity, understand supercosmic, eternal somethings? Well, Lewis gave it a shot. Perhaps this is exactly what is being depicted at the end of the 2nd book of the Space Trilogy, as the hero Ransom experiences what is known as the Great Dance prior to leaving Paralandra. Lewis writes, "The whole solid figure of these enamored and interanimated circlings was suddenly revealed as the mere superficies of a far vaster pattern in 4 dimensions. And that figure as the boundary of yet others in other worlds, till suddenly, as the movement grew swifter, the interweaving yet more ecstatic, the relevance of all to all yet more intense, as dimension was added to dimension, and that part of him which could reason and remember was dropped farther and farther behind that part of him which saw." This particular image that you see is an artist's attempt at rendering that quote from Paralandra. So I want to close this evening, and in closing, I want you to think about the quote that we began with from Lewis. He said, "Yet, though I could never have been a scientist, I had scientific as well as imaginative impulses, and I loved ratiocination." So my claim to you this evening is clearly Lewis possessed great powers of ratiocination and imagination. Hopefully I've demonstrated that to you. But what about a mathematical mind? What did Lewis have to say about mathematicians? By the way, Lewis's mother was trained in mathematics. Unfortunately, she died before he reached the age of 10, and so we're not sure what influence she had on him in this area. Here's what Lewis said about mathematicians. A mathematician's mind has a certain habit and outlook which is there even when he is not doing mathematics. So to test this claim, I suggest that you talk to the spouse of any mathematics professor. There are a couple in the room tonight, and you can see what they have to say. Even though Lewis could not tame the lion mathematics, his writings give evidence to the fact that his mind had that same kind of certain habit and outlook as that of a mathematician. So did Lewis have a mathematical mind, even though he couldn't do algebra? This mathematician says, yes, he did. Thank you.